Another problem here. So there is a resistance another resistance here. It is 2 ohms, it is 1 ohm, it is 1 ohm, it is 0.5 ohms, it is 1 ohm, it is I2 is this one, plus and minus it is V2, and he indicated this is I2 and this is I1, this one is I3. This voltage plus and minus it is V1, this is I1. So this is the problem. For this problem it is a resistive bridged T network. So for this problem what I need to find here is V2 by V1, V2 by I1, I2 by V1 and I2 by I1. It is not a bridged network, ladder bridge network. So whenever this type of non-ladder networks are present here, then how to solve this type of problems? Just you apply this mesh analysis here. For loop 1, if you apply the loop analysis, it is V1 is equal to this 1 plus 0.5, 1.5 into I1. It is I1, I3, both are in opposite direction, so it is first you consider this I2 here. I1 and I2 both are same direction here, so it is 0.5 I2. This I3 and I1 both are in opposite direction, so it is minus I3. So it is the first equation. For loop 2, so it is for loop 2. So it is plus and minus, it is plus and minus. So it is whenever current is flowing like this, plus and minus like this. So if I apply this loop analysis for this second loop, it is 1 plus 1 to 2.5. So it is if I take the current leaving terminal as consideration, minus 2.5 into I2, 1.5. If I add these three things here, that is 2.5. So it is minus 2.5 into I2. Next, this I1 and this I2 both are in same direction, so I need to consider this current leaving terminal here. So it is minus 0.5 into I1, and this I2 and this I3 in this both are in the same direction, so I need to consider the current leaving direction. Here it is minus I3 into 1 here, I3. So it is for loop 2. So if I write it equal to 0, if I rearrange it, 0.5 into I1 plus 2.5 into I2 plus I3 is equal to 0. Let us consider it is equation number 2. Next, for loop 3, so 1 plus 1, 2 plus 2, 4. So for loop 3, 4 I3. So this is plus and minus, it is plus and minus, it is plus and minus. So it is if I take current leaving direction, current leaving terminal here is taken as reference, minus 4 I3. Now this I3 and this I1 in this resistor, it is I3 is going like this, but I1 is going like this, opposite direction. So it is plus I1 into 1, this I1. But in this resistor, this I3 and this I2 both are in the same direction, so it is minus current leaving terminal. If I take current leaving terminal as same, current leaving terminal as reference here, minus this I2 here, I2 into 1, so it is I2, that is equal to 0. So if I rewrite this expression, I1 minus I2 minus 4 I3 is equal to 0. So it is equation number 3. So after writing these equations here, After writing these equations, let us write these expressions in vector matrix form. So vector matrix form, that is, what is this vector matrix form? It is v1 0 0 and it is 0, that is equal to this expression. Otherwise you keep it this one. If I multiply this, okay, not required, v1 0 0, and this one is 1.5, it is 1.5 I1, it is 0.5, so it is write it 0.5, it is minus 1, this is 0.5, second expression, it is 2.5, it is 1, and this is 1, and it is minus 1, it is minus 4, it is I1, I2, I3. If I find this I1 here, I1 is equal to delta 1 divided by delta as per Cramer's rule. What is this delta 1? If I replace this first column of this matrix with this column, then finding the determination of that one. So 0.5 is minus 1, it is 2.5 is 1, minus 1 minus 4 divided by this delta, that is 1.5 is 0.5, it is minus 1, 0.5 2.5, it is 1 1 minus 1 minus 4. If I find this I1 value, what I get here is, it is I1 is equal to V1. So if I find the determination here, I will get this one as 9V1 by 9, 9 will get cancelled. So finally what I get here is V1. So I1 is equal to V1 here. This is one expression that I got here. Let us consider it is fourth equation. Next thing, find I2 from this. If I find I2, use the Cramer's rule, delta 2 by delta, that is equal to determination. So replace this column with this column. 1.5 0.5 is 1, it is V1 0 0 minus I1 1 minus 4 divided by same this determination, it is 1.5 0.5 minus 1, 0.5 2.5 1, it is 1 minus 1 minus 4, that is equal to, if I calculate it, then I will get it is minus 1 by 3 V1. So I found this I2 is equal to minus 1 by 3 into V1. So it is expression, it is equation number 5. What I need to find here is V2 by V1. V2 by V1. Can I find this V2 by V1 here from these equations? No, I cannot find this V2 by V1. Is there any possibility to find V2 by I1? V2 by I1 also not possible. I2 by V1. I can calculate I2 by V1. I2 by I1. If I divide this expression with this, then I can get the I2 by I1 here. So I don't know the information about this V2 here. So from this network, V2 is equal to, this is the voltage plus and minus, and the current is flowing like this, so it is plus and minus. So V2 I2, I can provide the relation from the network. So from the network, from the network, V2 is equal to minus I2 into 1, that is equal to minus I2. So V2 is equal, this voltage is equal to this voltage. So it is I2 into 1 is the voltage. So V2 is equal to minus I2 into 1, that is equal to minus I2. So V2 is equal to minus I2. So I can find this V2 by I2. Okay, not required. So this is another expression here. V2 is equal to minus I2. So let us consider it is equation number 6. So from 4, 5 and 6, write this 4, 5 and 6 here. What I need to find, first V2 by V1. To find V2 by V1, V2 by V1. Okay. So from equations equations 5 and 6. 5 and 6. Divide these equations here. I2 is equal to minus 1 by 3 into V1 divided by this minus I2 is equal to V2. So this I2 will get cancelled here. So if this minus and this minus will get cancelled here. So V1 is equal to 3 into V2. So what I need to find V2 by V1, that is equal to 1 by 3. So first thing is over. Next V2 by I1. So to find this V2 by I1, so let us consider it is V2 I1. So I know the relation between V2 and V1 and V2. So from equation number 4, it is from equation 4, this is, let us assume it is 7. 4 and 7, I1 is equal to V1 value is 3 into V2. So what I need to find V2 by I1. So from this V2 by I1 is equal to 3. So second thing is over, V2 by I1 is over. Next I2 by V1. I2 by V1 can be calculated from the here itself, from 5. I2 by I1 can be calculated by dividing these two expressions. So from equation 5, from equation number 5, so I2 by V1 is equal to minus 1 by 3. So divide with this fifth equation, I2 by I1, I need to calculate I2 by I1. So equation 5 divided by equation 4, that is equal to I2 is equal to minus 1 by 3 into V1 divided by I1 is I1 divided by V1. This V1 and this V1 will get cancelled. So I2 by I1 is equal to minus 1 by 3. So whenever this type of non-laddered networks are present, this is the procedure for solving the problems. Okay, let us solve another problem here. So the problem here is, this is an impedance, and here also another impedance, and this is another impedance here, and there is another impedance is placed like this. Is plus and minus, it is V1, this is the current I1, this is the point A, this point is B, and this point is C, this point is D. This plus and minus, it is V2, it is ZA, it is also ZA, it is ZB, it is also ZB. Here what I need to find here is, I need to find Z11 comma Z12 and G12. So these things I need to calculate for this network. So first I'm going to redraw this network. This is important here. If you redraw this network, then it will become easier. See, this is a point. Let us take, this is the point A point. Okay, let us take it is A point, it is B point. So in between A and B there is an impedance whose value is ZA. So it is A, B. Between B and D, let us consider this is the D point here. B and D, there is an impedance whose value is ZB, it is ZB. And D and C, another impedance. Let us take, this is C point, so it is, this impedance is ZA. The impedance that is connected between D and C here is ZA. Now between C and A, another impedance ZB is connected here. it is ZB. Now between B and C, this is the voltage, that is V2. B point is plus and C point is minus, and from this A point, this is A point, this is A point, and this is D point, this D point. A point and D point, this was given to this input. So this is A point, it is plus and it is minus, it's V1, and this current is I1. So it is ZA, it is ZB, it is like this. So this same network I can redraw like this. So now what is Z11, what is Z12, and what is G12? Z11 is driving point impedance at port 1, that is Z11 is equal to V1 of S divided by I1 of S. Z12 of S is, it is transfer impedance, that is V2 of S divided by I1 of S. G12 is, it is the voltage gain, transfer voltage gain. G12 of S is equal to V2 of S divided by V1 of S. So these three things that I need to calculate from this network. So see here, if I write this expression, here it is open circuited, this V2, this part is open circuited. So this current, whatever the current is flowing like this I1 current will be deviating. Some current is flowing like this, some other current is flowing like this. Since there is no path available to flow in this direction, so whatever the current is flowing, the same current will flow like this. Here also the same thing, this current will flow like this, and these two currents will join here. So it is also I1, this I1, this is I1. Okay. Now it is, this impedance is ZA plus ZB, this impedance is ZA plus ZB, because these two are connected in series, So same impedances are there here and here, parallelly connected. So the current is also equally divided. Suppose it is I1, current is flowing. So now the current that is flowing through this is I1 by 2. The current that is flowing through this is I1 by 2. So equal current will be divided. Current will be divided equally in the same resistors connected in parallel. So now this voltage, so it is plus and minus, current is flowing like this, plus and minus, current is flowing like this. So now V1 is equal to, if I apply the KVL in this loop, I1 by 2 into ZA, I1 by 2 into ZA, this current into this impedance will give the voltage across this. So this current into this impedance will give the voltage across this. So it is the current flowing through this ZB is I1 by 2 into ZB. So that is I1 by 2, if I take a common, it is ZA plus ZB. So it is V1. So V1 is equal to I1 by 2 into ZA plus ZB. From this I can calculate Z11 of S, that is equal to 1 by 2 into or ZA plus ZB divided by 2 is Z11 of S. So this one I calculated here, ZA plus ZB by 2. Next, V2 and V1, V2 and I1. I need to provide the relation between V2 and I1. So this voltage, so this current is flowing like this. This is current, this is I1 by 2. So this current flowing through this is, it is I1 by 2. This current is I1 by 2. So this current is flowing in this direction, this current is flowing like this. So it is plus and minus, it is plus and minus. If I apply the KVL in this loop, if I apply the KVL in this loop, then plus V2, if I take the current direction, the current leaving terminal, this loop. So it is plus and it is minus here. Plus and minus, this one is plus and it is minus. Minus I1 by 2 into ZA, and current leaving terminal here. Sorry, it is plus here. Whenever the current is passing like this, it is plus and it is minus. So if I take the current leaving terminal here, it is plus here. So it is plus Z1 by 2 into IA. This one is current leaving terminal. If I take, it is minus I1 by 2 into ZB. That is equal to 0. So V2 is equal to I1 by 2, if I take it as a common, ZB minus ZA. So if you want to find Z12 is equal, Z12 of S is equal to V2 of S divided by I1 of S, that is equal to ZB minus ZA divided by 2. So this is Z12 of S. Next thing here is I need to find this G12 of S, or G12 is equal to V2 of S divided by V1 of S. So this is V1 of S, let us consider it as equation 1, and it is V2 of S, let us consider it as equation number 2. So equation number 2, equation 2 divided by 1, that is equal to V2 by V1, that is equal to this I1 by 2 into ZB minus ZA divided by this equation I1 by 2 into ZB plus ZA. So this I1 by 2 will get cancelled here. So V2 by V1, or V2 of S divided by V1 of S, is equal to ZB minus ZA divided by ZB plus ZA. So this is how we need to solve this type of problems.